Today we're diving into one of the most fascinating topics in condensed matter physics, Majorana zero modes in superconducting nanowires and engineered heterostructures. This is a frontier where quantum mechanics meets topology and where we might find the key to building robust quantum computers. Let me start with a fundamental question. What exactly is a Majorana mode? To understand this, we need to think about particles and antiparticles. In the standard model of particle physics, every particle has an antiparticle. For example, the electron has the positron, the up quark has the anti-up quark, and so on. Antiparticles have the same mass, but opposite quantum numbers like charge. When a particle meets its antiparticle, they can annihilate into pure energy. But in 1937, the Italian physicist Ettore Majorana made a remarkable prediction. He asked, could there be particles that are their own antiparticles? These would be neutral fermions, where the particle equals the antiparticle. Here's the key idea visually. Normally, a particle and its antiparticle are distinct objects. But a Majorana particle is special. It is identical to its own antiparticle. It's its own mirror image, in a sense. Now here's where it gets really interesting. We don't know if fundamental Majorana particles exist in nature. Neutrinos might be Majorana fermions, but that's still an open question. But in condensed matter physics, we can create effective Majorana particles as emergent quasiparticles in specially designed materials. These aren't fundamental particles, but collective excitations that behave like Majorana fermions. The key ingredient for creating these exotic states is superconductivity. Let me explain why superconductors are so special for this purpose. In a superconductor, electrons pair up into what we call Cooper pairs. These pairs behave like bosons and can all occupy the same quantum state, creating the superconducting condensate. Here we see electrons pairing up. The attractive interaction, mediated by lattice vibrations called phonons, causes electrons to bind despite their mutual repulsion. This pairing is the essence of superconductivity. In the superconducting state, there's a beautiful quantum mixing. The pairing mixes particle states, where we add an electron, and whole states, where we remove an electron. This mixing is crucial for Majorana physics. So how do we actually create Majorana zero modes? The recipe involves combining several ingredients in a careful way. Let me walk you through the standard approach. First, we need a semiconductor nanowire. This could be made from indium arsenide or indium antimonide. These materials have strong spin-orbit coupling, which is essential. Second, we place this nanowire in contact with a superconductor, typically aluminum. The superconducting pairs leak into the nanowire through a process called proximity effect, inducing superconductivity there. Third, we apply an external magnetic field along the nanowire. This field breaks time reversal symmetry and is crucial for entering the topological regime. Fourth, we use gate electrodes to tune the electron density and chemical potential in the nanowire. Getting this tuning right is critical for reaching the topological phase. Here's a schematic of the device. We have the semiconductor nanowire on top of the superconductor. The magnetic field points along the wire axis. Gates control the electron density. And crucially, Majorana zero modes appear at the two ends of the wire. Now here's where things get truly weird. Let me explain the non-local nature of these Majorana modes. A regular electron is a complex fermion, with both real and imaginary parts to its wave function. A Majorana mode can be thought of as just the real part or just the imaginary part. It's like splitting the electron into two pieces. The remarkable thing is that the Majorana modes at opposite ends of the nanowire together constitute a single non-local fermion state. The occupation of this fermion state can be either empty or filled, giving us two quantum states. Mathematically, if C is a regular complex fermion operator, we can write it as C equals gamma 1 plus I times gamma 2, where gamma 1 and gamma 2 are the two Majorana operators living at opposite ends. This non-local encoding is the key to topological protection. Local perturbations at one end can't easily flip the quantum state because the information is stored non-locally across the entire device. The two ends are too far apart for local noise to affect both simultaneously. Here's the protection mechanism visually. Local noise at one end disturbs gamma 1, but the quantum information encoded in the occupation of the full fermion state, which involves both gamma 1 and gamma 2, remains protected as long as the wire is long enough. Let me explain why these modes are called zero modes. This is connected to their topological nature. In the topological superconducting phase, the Majorana-bound states sit exactly at zero energy in the middle of the superconducting gap. They're not just approximately at zero energy, they're pinned there by topology. There's an energy gap between these zero energy modes and all other excited states. This gap, typically the superconducting gap, provides an energy scale for protection. Thermal fluctuations below this gap energy can't create unwanted excitations. The energy of the Majorana zero mode equals exactly zero. The energy gap delta E is on the order of the superconducting gap delta zero, typically around 1 millielectron volt. Now let's discuss the experimental evidence. How do we actually detect these Majorana modes? What signatures do experimentalists look for? The primary signature is a zero bias conductance peak. When you tunnel electrons into the device and measure conductance versus voltage, you expect to see a sharp peak exactly at zero voltage bias. This is what the zero bias peak looks like. You have voltage on the horizontal axis and conductance on the vertical axis. At exactly zero bias, there's a sharp peak in conductance. This happens because the Majorana mode provides a resonant channel for electron tunneling. The theory predicts that this peak should have a quantized height. At zero temperature and perfect coupling, the conductance should be exactly 2e squared over h, where e is the electron charge and h is Planck's constant. The peak conductance, G peak, equals 2e squared over h. This is a fundamental quantum of conductance. Another key signature is that the zero bias peak should remain pinned at zero energy even as you change external parameters like magnetic field or gate voltage. This robustness is a hallmark of topological protection. The splitting between the two Majorana modes should decay exponentially with the length of the nanowire. Longer wires give better separation and stronger topological protection. Now I need to be honest about the current state of the field. The experimental evidence for Majorana modes is intriguing, but still hotly debated. Let me explain why. The main challenge is that zero bias conductance peaks are not unique signatures of Majorana modes. Other phenomena can also produce similar peaks, making interpretation difficult. For example, ordinary Andreev-bound states, which are particle-hole symmetric states at finite energy, can sometimes appear to give zero bias peaks if there's disorder or if parameters aren't perfectly tuned. Real devices have disorder in the semiconductor, smooth electrostatic confinement from gates, and imperfect interfaces. All of these can create states that accidentally sit near zero energy without being true topological Majorana modes. Many experiments see zero bias peaks, but they often don't show the predicted quantized conductance. The peaks might be broader than expected or at the wrong height. This raises questions about whether we're really seeing Majorana modes. Some groups have reported that these signatures are sensitive to cool-down cycles and can disappear and reappear in ways that are hard to explain if they're truly topological. This suggests that trivial physics might be playing a role. However, recent experiments have become more sophisticated. Researchers are now looking at multiple signatures simultaneously, studying how peaks evolve with parameters, measuring non-local correlations between wire ends, and using improved materials and fabrication. This is the current state of affairs. We have intriguing evidence on one side, but also legitimate concerns on the other. The scientific community is actively working to resolve this debate through better experiments and theory. Now let me explain why physicists are so excited about Majorana modes, even with the experimental uncertainties. It's all about topological quantum computation. Traditional quantum computers use qubits that are extremely sensitive to environmental noise. Any interaction with the environment causes decoherence, destroying the quantum information. This is the main obstacle to building large-scale quantum computers. Topological qubits based on Majorana modes store information non-locally in the occupation of fermion states formed by pairs of Majoranas. This non-local encoding makes them inherently resistant to local perturbations. Here's the key idea for computation. You can perform quantum gate operations by physically moving or braiding the Majorana modes around each other in space and time. When you exchange the positions of two Majorana modes, the quantum state of the system changes in a way that depends only on the topology of the path they traced out, not on the precise details of how you moved them. Here's a schematic of braiding. You start with gamma 1 on the left and gamma 2 on the right. You move them in a crossing pattern, with gamma 1 going to where gamma 2 was, and vice versa. This braiding operation performs a quantum gate on the encoded qubit. The beauty is that small errors in how you move the Majoranas don't matter. As long as the topology of the exchange is correct, the quantum gate is performed perfectly. This is called topological protection of quantum information. I should mention that braiding alone with just Majorana modes doesn't give you universal quantum computation. You need additional operations, possibly through measurements or by combining with conventional qubits, but the Majorana operations provide a highly protected subset of gates. Let me paint a picture of what a Majorana-based topological quantum computer might look like if we can get the physics to work reliably. You'd have an array of superconducting nanowires, each hosting Majorana zero modes at their ends. Each pair of Majoranas encodes one qubit. You need the ability to turn on and off couplings between different nanowires. This could be done with gate electrodes or movable components. These couplings allow Majoranas from different wires to interact. You need to be able to measure the occupation of the fermion states, either through tunneling spectroscopy or other measurement schemes. This allows you to read out the qubits. The whole system needs to operate at ultra-low temperatures, typically below 1 Kelvin, to maintain the superconducting state and minimize thermal excitations above the gap. This shows a conceptual architecture, multiple nanowires arranged in an array. Each has Majorana modes at the ends. The nanowires can be coupled to perform braiding operations and create an entangled topological quantum processor. Even if we conclusively demonstrate Majorana modes, there are still significant challenges to overcome before we have a working topological quantum computer. Creating 1 or 2 Majorana qubits is one thing, but scaling to hundreds or thousands of qubits needed for useful quantum algorithms is an enormous engineering challenge. While topological protection helps, it's not perfect. During the physical braiding operations, which take finite time, there can still be diabatic errors or unwanted couplings to the environment. You need exquisite control over when and how different Majorana modes are coupled. Any unwanted couplings can lead to errors in the quantum gates. There's a trade-off. To maintain topological protection, you want large separation between Majoranas, but this makes braiding operations slower. You need to balance protection against operational speed. I should mention that semiconductor nanowires aren't the only platform being explored for Majorana physics. Let me briefly describe some alternatives. Topological insulators have conducting surface states with special properties. When you place a superconductor on a topological insulator surface and apply a magnetic field, you can potentially create Majorana modes at vortex cores or domain walls. Another approach is to place chains of magnetic atoms on a superconductor surface. The interplay of magnetism and superconductivity can create Majorana end states. This was demonstrated beautifully with iron chains on lead. In two-dimensional electron systems at very high magnetic fields and specific filling fractions, exotic quasiparticles with non-Abelian statistics can emerge. Some of these may host Majorana-like modes. Nanowires offer tunability and potential for device integration. Topological insulators have cleaner surfaces. Atomic chains give atomic scale control, but are hard to scale. Fractional quantum Hall systems have beautiful physics, but require extreme conditions. Students often ask me, if Majorana modes are so fragile to detect and create, why are we so confident they're the right approach for quantum computing? That's a great question. The key is that topological protection is qualitatively different from conventional error correction. In conventional qubits, you need to constantly monitor and correct errors. With topological qubits, the protection is built into the physics its. Even if real-world Majorana modes aren't perfectly topological, if they retain some of that protection, they could still offer significant advantages in error rates compared to conventional qubits. The quantum computing field is pursuing multiple approaches in parallel. Superconducting qubits, trapped ions, silicon spin qubits, and topological qubits all have different strengths. Having multiple paths increases our chances of success. Let me highlight some of the most exciting current research directions in Majorana physics. Researchers are developing cleaner semiconductors with higher mobility, sharper interfaces with superconductors, and better control over disorder. Materials science is crucial here. Beyond zero bias peaks, physicists are developing new ways to detect Majorana modes, including measuring non-local correlations, studying Coulomb blockade effects, and using microwave spectroscopy. Several groups are working toward the first experimental demonstrations of braiding Majorana modes. This would be a landmark achievement, showing that we can actually manipulate these states to perform quantum operations. There's growing interest in hybrid systems that combine Majorana qubits with conventional qubits. This could give you the best of both worlds: topological protection for some operations and fast gates for others. Let me step back and explain why this research matters beyond just building quantum computers. Majorana modes in condensed matter represent genuinely new states of quantum matter with no classical analog. Understanding them deepens our knowledge of what's possible in quantum systems. The idea that topological properties can protect quantum information has revolutionized how we think about robustness in quantum systems. This insight extends far beyond Majorana modes. The heterostructures used to create Majorana modes showcase our growing ability to engineer quantum materials with desired properties. We're learning to be architects at the quantum level. If successful, topological quantum computers could solve problems in cryptography, drug discovery, materials design, and fundamental physics that are impossible for classical computers. Let me give you an analogy that captures the weirdness of Majorana modes. Think of the Cheshire Cat from Alice in Wonderland. A regular electron is like the full Cheshire Cat. A Majorana mode is like the cat's grin separated from its body. Each piece, the grin and the body, exists independently at different locations. Together they make up the cat, but separately they're incomplete. That's what it means to split a fermion in half. Students also ask me, when will we have topological quantum computers? Let me give you a realistic assessment. In the near term, the next 2 to 5 years, the goal is to conclusively demonstrate Majorana zero modes with multiple unambiguous signatures and to show basic braiding or fusion operations. In the medium term, 5 to 10 years, we might see small topological quantum processors with a handful of qubits demonstrating quantum algorithms with topological protection. In the long term, beyond 10 years, if the approach proves viable, we could see scalable topological quantum computers competing with or complementing other quantum computing platforms. I must emphasize the uncertainty. It's possible that despite all efforts, the approach won't be practical, or that other quantum computing approaches will win the race. Science doesn't guarantee success, but the journey teaches us regardless. Let me summarize the key points from this lesson on Majorana zero modes. First, Majorana modes in condensed matter are emergent quasiparticles that are their own antiparticles, a property predicted by Majorana but realized in engineered quantum materials. Second, these modes can emerge at the ends of semiconductor nanowires with proximity-induced superconductivity, strong spin-orbit coupling, and an applied magnetic field. Third, the quantum information is encoded non-locally across pairs of Majorana modes, providing intrinsic protection against local sources of decoherence. Fourth, braiding operations, where Majorana modes are physically exchanged, can implement quantum gates that are protected by topology. Fifth, while there is intriguing experimental evidence, including zero-bias conductance peaks, the interpretation is still debated, and more definitive signatures are needed. Sixth, if successful, topological quantum computers based on Majorana modes could be far more robust to errors than conventional qubit designs, potentially solving the decoherence problem. Let me close with some reflections on the scientific journey we're witnessing. The search for Majorana modes exemplifies modern physics at its best. Deep theory meeting sophisticated experiments with profound implications if successful. The controversies and debates are not weaknesses, but signs of a healthy scientific process. Extraordinary claims require extraordinary evidence, and the community is working hard to establish that evidence. This research brings together condensed matter theorists, material scientists, experimentalists, and quantum information theorists. Progress requires all these perspectives. We don't know yet if topological quantum computers will succeed, but regardless, we're learning to manipulate quantum matter in unprecedented ways. That knowledge will have value however things turn out. Thank you for joining me in this deep dive into Majorana zero modes and topological quantum computation. This is one of the most exciting frontiers in physics today, where fundamental theory meets cutting-edge experiments and practical applications. The next few years will be crucial in determining whether this beautiful idea can become reality. The story is still being written, and you could be part of writing it.